Welcome back my dear friends and dear students. A very good morning, good afternoon, good evening to all of you, and this is the DADM, which is Data Analysis and Decision Making course under NPTEL MOOC. This is the DADM 1 course under MOOC, and we are in this 52nd lecture, which we have just started the second lecture for the 11th week, and we have another 1 week to go before we wrap up with the course. As you know, this is a 12-week course, total number of hours is 30, total number of lectures is 60, because each lecture being for a half an hour, and each week we have 5 lectures, and this is half an hour each, and my name is Raghunandan Sengupta from the IME department, IIT Kanpur. So, we were discussing about loss functions, and I mentioned that for loss functions initially they are quadratic. Why quadratic? We consider that they have a one-to-one simile with respect to trying to minimize the variance, and if the theta value is an unbiased estimation for t is the estimate which you get from the sample, then finding out the difference, squaring it up and finding out the expected value of that would give me the loss, which is the variance. Trying to minimize the variance obviously is the best way we can achieve. Then we consider that we have the linear loss function, where you give, if you give equal penalties to t minus theta or t minus theta on the negative side or theta minus t, whichever way you denote, and if k1 k2 which are the weights are equal, which is equal to 1. So, it is a 45 degrees line in the first quadrant and the second quadrant, and in case if k1 is more than k2 or k2 is more than k1, we will give weightages accordingly. That means, overestimation is more penalized or underestimation is more penalized. And then later on we also discussed through the diagrams obviously that in case if k1 k2 are functional forms of theta also, which means for higher values of theta or lower values of theta, your overall weightages for the loss function may change rapidly. That means, higher the values are, more the weights are, that means k1 keeps increasing. Maybe this increase can be linear, maybe this increase can be non-linear over and above the loss functions concept which we are also discussing. And then if underestimation is more penalized or less penalized, the values of k would also change accordingly, but consider k I am using just a symbol. So, k by itself is basically a functional form of weights for the thetas or the domain in which we are trying to basically find out the theta. Then later on I in the last few minutes of the 50th lecture, I did mention that what if the loss function is of the form, it is basically the probability or the difference between t minus theta, and it has a one-to-one correspondence with the concept of interval estimation, and this difference being will be loss function will be equal to 1 if t minus theta is greater or less than equal to epsilon. So, that greater than or less can be modeled accordingly, and in case it will be otherwise it will be 0. So, here we are considering the mod means equally distance from the mean value onto the right or the left, and they give us very good results corresponding to the fact that we want to find out something to with these loss functions and the interval estimation problems. So, 52nd lecture is about the loss functions. Now, Arnold Zellner in 1984 proposed the balanced loss function. So, balanced loss function is more to do with the regression or multiple linear regression concept. So, when we are doing the multiple linear regression, I always emphasized and I have been talking that you find out the difference of the square of the difference for the which is basically the errors, square them up and then differentiate with respect to parameters, put those values into 0, find out the parameters in a hat form, which is the estimated form, and complete the set of other tests which you want to do, and but the main part is over for the studying that. Now, in case of the multiple linear regression, what we considered is that these values of the differences which we take for t minus theta, or here theta can be, say for example, beta is theta and beta hat is t, or it can be, say for example, beta 1, beta 2, beta 3 are the corresponding values of theta 1, theta 2, theta 3 considering as a vector. In that case, t 1, t 2, t 3 would be the corresponding estimated values for theta 1, theta 2, theta 3. Now, in Arnold-Zellner proposed that what about trying to basically give weightages for the loss function based on two important aspects. One is basically the estimated value which you find out, and based on the estimated values of which you found out, which is for alpha and beta, then you find out y hat, which is basically the best forecasted value of y. What if we give weights to those the difference of the errors corresponding to y hat and y. That means, you are going two step. First, trying to basically find out the parameters values using the estimated values, then try to basically give some weightages to the loss function corresponding to theta and then utilizing some other concept of loss function corresponding to y and y hat. Now, in case if the corresponding loss function with respect to theta and n is basically quadratic. So, obviously, it would be quadratic loss function, and in other case again if it is quadratic, in order to find out the differences or find out the errors of the differences between y, which is the actual value, and the predicted value is y hat, then we will basically have the balanced loss function. This is what we are going to discuss about. The balanced loss function reflects both goodness of fit, which is the lack of bias, and the precision of estimation. So, there are two steps. One is the precision of estimation, how precise your estimation is, and then how good your model basically fits in order to compare the estimated value, which is y hat, with respect to the actual value, which is y. So, y and y hat can be scalar, and y hat can be vector also, depending on that you have different values to predict utilizing the values of x 1, x 2, x 3, x p. A balanced loss function as proposed by Zellner would basically have two parts. So, one is basically the weightages which you have, which is w for the first part and 1 minus w for the second part. So, what is basically the first part? So, if you let me highlight it. So, this if I consider is basically the goodness of fit which I am considering. So, how good or bad the fit is. So, here you basically have g theta, which is the functional form of theta, which can be, say for example, y also, which is the actual value, and g functional form of t would basically the y hat which you want to find out. So, here what you are trying to find out is the difference between y and y hat. As an example, I am giving, squaring them up, putting some weights, which is w. So, this is basically the goodness of it. Let me highlight it with a yellow color. Now, let me come to the precision of estimation. This is the estimation which you want to find out. Let me change in the color. So, in this case, the precision of estimation was basically again a squared concept, which is basically the difference between theta and t, or in multiple linear regression it will be basically the difference of alpha and alpha hat, or beta and beta hat, whatever it is, based on the either the univariate case, if it is a simple linear regression, or the multiple linear regression, whatever it is. And this is basically the precision of estimation, where you give a weightages of 1 minus w. Now, it should be remembered that Arnold-Zellner proposed the balanced loss function such that the weights basically add up to 1, because you, depending on the penalty which you want to put, both for precision of estimation as well as for the goodness of it, you will give weights accordingly. The first term basically represents the goodness of fit, as I mentioned, where the second term represents the precision estimation, how good or bad your estimation is. So, which is also termed as the accuracy. So, the in case what can be done. So, now I will again create a blank slide and explain few things. So, first term I am again coming back to my lecture. The first term represents the goodness of fit, while the second term represents the precision of estimation, which is also termed as the accuracy. The second term, as originally used by Zellner, consists of in its quadratic form or the squared error sort of form which is there, which means what did Arnold-Zellner consider would be like this. So, your balanced loss function I will consider is suffix BLF, loss function which is balanced loss. I will give weights W, and here I am considering that the precision of estimation and the goodness of fit. Goodness of fit is basically with respect to y and y hat. So, I will put y minus y hat, it is squared. So, because that was g theta minus g t transpose into g theta minus g t values, that is why it is basically square, plus 1 minus w I am giving the weights to the precision of estimation. Precision estimation would be, say for I am considering a very simple concept. I am considering there is, say for example, only one theta you want to find out, which is the simple linear regression. So, that case it will basically be b minus b hat. So, this would basically be the precision of estimation, this would basically be the goodness of fit, and the loss function, balanced loss function can be made accordingly. So, say for example, if you remember, I considered what are the very simple loss functions I considered. I considered the linear loss function, the weighted linear loss function, the 0-1 loss functions. So, the problems can be structured. I will use another different color. Say for example, the balanced loss function can be it, say for example, I will consider y minus y hat without the square, which is basically linear function, plus 1 minus w by beta minus beta hat whole square. So, in this case this is quadratic and this is not quadratic. So, this is basically linear, or it can be reversed also, that means the linear part goes through for the second part, precision or estimation, and the square part comes into the goodness of fit. Or else it can be like, let me use another the balanced loss function can be, if you consider the 0-1 loss function. So, it will be probability of the difference y minus y hat being less than equal to epsilon. So, this can be 0 and 1 plus 1 minus w or omega, whatever it is. So, this is beta minus beta hat, this is square, and based on that you proceed. So, again here the precision or estimation is quadratic, while the goodness of fit is basically the 0-1 loss function. It can be again changed, like the 0-1 loss function goes to the precision of estimation and the quadratic part comes into the goodness of fit. So, there can be different variants of the loss function, but obviously there has to be some theoretical niceties in what you want to achieve and the practicability of the problem. So, this is this was the blank slide, I kept it purposefully. Okay. Now, let us continue the discussion. So, the least square estimation reflects the goodness of fit considerations, whereas the use of quadratic loss function involves a sole emphasis on the precision estimation. So, that will depend on the type of problems which you have. So, depending on the problem, these terms can be modified into linear loss function, as I mentioned. It can basically be the mod loss function, it can be quadrilateral loss function, it can be any sorts of loss function, both for the goodness of fit and the precision of estimation. Now, Hall variant in the year 1975 used this loss function, which is known as the Linux loss function, which is linear exponential loss function. So, Linux, the word Linux which is coming is for the part it is linear. Oh, I should use the highlighter, my apologies. So, this is Linux. So, this is the LINEX, Linux loss function. So, sorry, this double E will not come. I will use this also. That is the Linux loss function. Now, in the Linux loss function, as the word mentions it, there are two parts, which is the linear part and the exponential part. On Hall variant, you first employed such a loss function in the real estate assessment in order to basically find out the prices and the populations and so on and so forth. But later on the work was left to Arnold Zenner also again, who basically found out all the statistical properties of that. So, now here comes basically the actual description. The fact that overestimation and underestimation of theta, which is the parameter of the population, may be of unequal consequences, unequal importance, higher means more penalty, lower means less penalty, or it may mean that lower being more penalty, higher being less penalty. What I mean by high and low is basically the difference of the estimated value and the actual value, which is T n or T minus theta. Theta is basically the parameter value and T or T suffix n is basically the estimated value for theta. The fact that overestimation and underestimation of theta may be of unequal consequences has not been properly or adequately emphasized in any of the above loss functions. So, based on that we will try to basically proceed and learn something about the Linux loss function. So, as I was discussing, after Hall-Varian, this work was taken up with Arnold Zenner and he proposed the loss function. A loss function which takes case of this is the linear exponential loss function, the Linus loss function, which is Zenner 1986, which is given by the asymmetric convex loss function, and it is of this form. So, here L delta, well, delta is basically the difference between T minus theta or theta minus T, in whichever you try to basically portray. So, they would basically be before I discuss the loss function, they would be two parameters. One is basically A, which is the shape parameter, and theta, and B is basically the scale parameter, depending on the shape and scale how it can be changed. Now, the loss function basically consists of the linear part, which is here, and the exponential part, which is here. So, hence it is known as a linear exponential loss function. Now, notice very interesting thing, if the difference between T and theta is very small, that means you are trying to basically estimate or find out the loss corresponding to very precision of estimation, very precise. Precision of estimation I am not talking from the viewpoint of balanced loss function, is very precise, very nearby. Then look at the exponential term, expand it. So, if you expand it, if we know the expansion of e to the power x is basically 1 plus x divided by 1 factorial plus x square by 2 factorial, and it continues. So, if you basically expand it, e to the power a t minus theta, the first term would be 1 cancels here, then the second term here is basically plus a t minus theta. So, that term and this second term which I am highlighting now also cancels, and if you consider the squared error term, that means the third term, which is squared error term, is only important and other terms becomes very less, because when I mentioned that the difference between the estimated value and the actual value T n minus theta is very small, hence the cube root, fourth power root, fifth power root can all be ignored. So, what we are left is basically the quadratic form. So, hence if you see that the linear exponential loss function for very precise estimation can be converted into a squared error loss depending on the practicality of the problem. So, here as per the Zellner I am just reading it, that functional form basically consider B is not there, it would not make much sense, because B being a parameter which serves to scale the loss function depending on how you are trying to tackle the problem. So, again I will again repeat, there is a linear part, there is an exponential part, and we saw that the Linux loss function can be converted into a quadratic loss function depending on the efficiency or the precision of estimation, considering that the third power onwards, which means that cubic power and onwards would basically be ignored. When A is greater, so obviously here is where the asymmetricity will come for the loss function, and it will be very clear to all of us. So, if A is positive, large number, then in that case exponential part would be dominating the linear part for the right hand side of the values of the difference between t and theta, such that delta is positive, because if delta is positive, so obviously and A is also positive, then the exponential part will dominate the linear part, Hence, here overestimation would be more of a problem, more of a concern. And in this case, in the case which you are talking about, if A is positive, obviously in the negative zone where t minus theta is negative, obviously that exponential part would not be dominating the linear part, hence it will be more or less linear in nature in the second quadrant. I will come to the graphs later on, please wait. But in the other case, if we consider, say for example, the values of this A is negative. So, if A is negative and again you are considering t n minus theta as positive. So, obviously the exponential part would not be dominated by the linear part, and the linear part and the exponential part when combined together, in that case, so called for our understanding we will say then that the overestimation is less penalized. But if I consider in the underestimation, in this case we have already have the difference between t n minus theta as negative, A is also negative. So, negative would make it positive, hence you have a exponential part which would be increasing exponentially in the second quadrant, that means for underestimation. So, hence for A values as positive, overestimation is more penalized, for A values as negative, underestimation is more penalized. So, obviously, we will be asking that what are the different type of examples which we have, I will come to that later on. When A is greater than 0, the convex loss increases almost linearly for negative errors, which is theta delta, which is t minus theta, and almost exponentially for the positive errors, which is t minus theta. Therefore, overestimation is a more serious consequence than underestimation, as I just mentioned. When A is negative less than 0, the linear exponential increase and decrease, they are swapped within each other, they are interchanged, whereby the underestimation becomes more serious than overestimation. So, obviously, you will basically formulate your problems accordingly. So, this is the loss function, which is basically looks like this. I think I should draw it, wait. So, it will look like, if overestimation is more penalized, I will use a different color. Overestimation is more penalized, then so this would be more, this would be less. And in case if it is underestimation is more penalized, so this will be the loss function. So, obviously, in this case A is less than 0, in this case A is greater than 0. Based on that, you will try to do the calculation. So, here if you see A greater than 0, overestimation more penalized and underestimation less penalized. Here if you see for A value is less than negative, underestimation is more penalized and overestimation is less penalized. So, and obviously, this one should remember delta value is basically t minus theta, and the loss function is also modeled accordingly. So, let us consider simple 3 examples. Consider a company plans to launch a new product, say a refrigerator in the market, and it is in the consumer market. Based on this which you want to pursue, and also suppose the similar products from different manufacturing companies already exist in the market. So, obviously, when the company wants to float the problem, let me tell you the background. So, obviously, there would be warranty life. So, warranty life means that if the product fails before the warranty life, you are liable to change and replace the product as per the norms of the company, and in case if it fails after the warranty life, obviously the person will basically make the payments and change the product accordingly. Now, the issue is that if it is a new product and there are such other products, good competitors in the market who are also new, and you want to basically go for a warranty life which will basically give you the best possible action. That means, maximum the products would not fail during the warranty time within, and it will start failing after the warranty time. So, people would be making the contracts accordingly. Now, consider the warranty life is, say for example, 6 months, arbitrarily consider, and in case 1 and case 2, in case 1 you give a warranty life of 8 months, and in case 2 you give a warranty life of 4 months. Now, if I consider 8 months is 2 plus 2 more than 6 and 4 months warranty is minus 2 with respect to 6 months, which is the actual warranty. Now, if your actual penalty is quadratic, so in that case 8 minus 6 which is plus 2 whole square and 4 minus 6 which is minus 2 whole square would give you a penalty which is quadratic, which is squared error loss, and obviously the penalties both for positive and negative would be of equal amplitude, which is fine for our calculations, but we are not taking practicality into consideration. Consider the product basically which you are going to sell. If you give up a warranty which is higher, so what will happen is that in the initial period people will be more willing to buy your products because your products warranty life is much higher than the rival products. But consider on the other hand, maximum of the products, say for example, in case if the warranty life is actually not 8, it is less than 8 and basically products start failing, which means that even if initially people bought your product in large numbers, but the failure rate has increased, that means you have to basically replace them or pay the penalty by either buying those products again back to them or basically replacing those expensive parts, whatever it is. So, initial profit or revenue has basically been offset by the case that you have not been able to predict the warranty life as it should have been, which is basically in and around 6, but you gave a estimated value of 8. So, there the losses would be different and they would not be quadratic, they would be unequally penalized. Now, consider the other case where if your warranty life actually should be 6, but you gave 4, which means that people would be more willing to buy your rival products. You will lose a huge amount of market in the initial set, but obviously it may happen that if the products actually are nearer to the actual value which you should have been predicted. So, obviously later on you will slowly gain some of the market share, that means again it is unequally penalized. Now, consider this, I will read this slide and then again give another example. So, consider a company plans to launch a new product, say a refrigerator in the consumer market. Also suppose the similar products exist from different manufacturers which already exist in the market. So, this is the background which I already mentioned, I am going to read it again. Consider then the company is expected to give such a warranty for the particular product, that is the refrigerator, to its customers in order to sell the product in the market, which is fine, they should give warranty. Now, if the value of this warranty is more than the average time of failure for the product, then the aforesaid mentioned company needs to replace the damaged product it sells or face basically litigation action by the customers. On the other hand, if the warranty period is less than the average failure of the similar products in the market, then the company loses the market share to its rivals, as naturally the customers are willing to buy the refrigerator from the competitors who assume a higher warranty life. So, as I said that if your warranty life is less than the average life, then the companies would lose the initial market share. So, all of them will go to the rival party or the other manufacturers. But even if they are willing to come back later on and to buy your products, but this amount of offsetting would definitely not be possible in order to take care of your loss. So, what values of A or whether it is positive or negative you would give for this example will depend on what your over estimation and underestimation problems would be with respect to the estimation problems which you basically would have done. So, this is a refrigeration problem, we will see later on, it can be an electrical problem, it can be a civil engineering problem, and based on that we will study that how loss functions can be utilized. So, with this I will end this 52nd class, and in the 52nd class I just considered the Linux loss, a simple example of the refrigerator, and continue 2 more examples in the, as I said, in the electrical engineering, the civil engineering case in the 53rd class, and continue more discussion about the multivariate statistical models and other methods. Thank you very much and have a nice day.